We're going to do a lot of tricks with the Van de Graaff in this unit. It's a beloved instrument because it creates large static charges, and those do cool things. They can make people's hair stand on end. They can make things go shooting off the Van de Graaff. They can even make a bell ring. And we'll spread these demonstrations out, and we'll try to use them to understand something complicated, like maybe induced charge or the concepts of voltage and electric field. The first demonstration is one of my favorite ones, though, and it's used to teach the idea that when you have charges in a conductor, they spread out as far away from each other as they can possibly get. And that's based on something you've known for a long time, that like charges repel each other. But the consequence is pretty important. If you have a charged conductor, the charges will be on the outside. So here's the demonstration of this. When I charge up this Van de Graaff ball, the charges are going to go all around the dome. I'm going to drop these conductive piepans right on top of the dome. I want you to watch what happens. Give it a little while to charge up. On a very dry day with a very big Van de Graaff ball, you can get these things going shooting off. But that was a pretty good demonstration. So discharge the Van de Graaff, and now we'll try to explain what just happened. We can see here the running Van de Graaff generator with its positively charged dome. And one of the principles of charges in a conductor is that they will arrange themselves to get as far away from each other as possible. That's why I have them spread outside the surface of the dome. But when we put the pie plates on, now there's even farther away from each other they can get because some of the charge can move into the pie plates. Now this may seem a little bit weird because you guys know that the positive charges are located in the nuclei of atoms. They can't move. The reason positive charges rearrange themselves in conductors, though, is that the electrons, the negatives, can move, and they're going to redistribute themselves to get the positive charge as far away from each other as it possibly can. So I think I have to show you what I mean by that. So if this is running and I throw these neutral pie pans on, in the top pie pan, an electron is going to go scooching all the way down, and it will cancel out one of these positive charges. Now, of course, when that happens, it's going to leave the pie pan positive. And that's going to keep happening, and since the Van de Graaff is going to keep running, positive charge is going to continually be created, and positive charges are going to show up all over this outer pie plate. Maybe there won't be as many here. So that would be fine, except that these parts here are also on the outside of the stack, and they're going to acquire a positive charge too. And since you guys know positives and other positives repel each other, that's going to put an upward force on the top pie plate. And the process is just going to repeat itself until every plate is gone. So it's an elegant representation of the fact that charges can move around in conductors, and charges will rearrange themselves so that they line up on the outermost place they can get, because that's as far away from other charges of the same type as they can be from each other.